Hello, everyone. I'm Nick Gerace. I'm a software engineer at SUSE, formerly at Rancher Labs, and today I'm going to be talking to you about Rust in Userspace in a cloud-native world. See, most of my day-to-day work involves working on Rancher, which is written in Go, as well as many other parts of the cloud ecosystem, which are also written in languages like Go, Python, Node, and Ruby. But today we're going to go a little off the beaten path and talk about Rust specifically for the cloud-native use case. If you have any questions after the talk, because I know this is going to be pretty fast paced because we have a lot to cover, feel free to reach out to me on Twitter. My handle is right here on the title slide at NickGeraceHacks, and send me a tweet. So the goal for today's talk is to get you writing some cloud native Rust code. You can evaluate it for your org, your team, or your use case, but I want to help you get to that point where you can start writing some cloud native Rust code and see if it's right for you. And these are the things we're not going to be covering. We know that Rust is very popular. And yes, this is a technical beginner track. So a quick Google search may show you Rust is very popular. It's in every post. It's all over, it seems, right now. And, they talk about the borrow checker, compiler messaging, all this great stuff. There's a Rust Foundation with a bunch of organizations, and there's some engineers that talk about it a bit too much, but we're not going to cover these things, really. We're going to go over some of Rust strengths, but not really focus on it over everything, just for the cloud native use case. So today we're going a bit off the beaten path, actually. We're going to be focusing on the fact that many organizations choose Rust for embedded and OS use cases, specifically where C and C++ has previously thrived. But we're going to see why that's the case and explore why use Rust in Userspace for cloud native applications as well. And those use cases involve technologies like containers, Kubernetes, immutable operating systems, and things that SUSE does, like OpenSUSE MicroOS and Rancher. And then we're going to be talking about my experiences writing certain applications and services for Kubernetes. And then we're going to use the blood, sweat, and tears from that to transition towards how and where to get started. And these will be things like, how do I build static binaries, recommended libraries, and just general tips. So yes, we're going off the beaten path, and we're covering cloud native in particular for Rust. So we're going to split this up into 4 sections. Why Rust in Userspace, exploring Rust present and future in a cloud native world, my experiences, particularly 2 writing cloud native Rust, and then finally we're going to end off with the how and where to get started, just like we talked about last slide. So the first things first, let's talk about why Rust in Userspace, specifically for cloud native use cases. And you can see there on the bottom, I put the cargo build release in the format of the 4, so whatever. Okay, so by the title of the slide, you might be thinking, oh man, this guy probably went to a liberal arts university, and you would be correct. I love semantics. So let's agree on some definitions from Wikipedia. I'll try not to use Userspace and cloud native interchangeably in this talk because they're entirely different. We want to follow experiences writing Rust in Userspace and why to do that in order to satisfy our cloud native use cases. So when we talk about Userspace, we're talking about the memory area where application software and some drivers execute. And when we talk about cloud native, we're talking about building and running scalable applications in private, public, and hybrid clouds, specifically in capacities like containers, microservices, serverless, immutable infrastructure that are deployed by declarative code. I'll try not to use them interchangeably, but just know that dichotomy as we go throughout this, because that is an incorrect usage, but we're going to try to make this as correct as possible as we go through. So I don't want to focus on the history too much in the interest of time, but Rust started as Graydon's personal project in 2006 at Mozilla and became stable in 2015. It was a little older than even I expected. And its number one feature, in my opinion, is the borrow checker. And I like to think it offers automatic memory management without a garbage collector. So essentially, you get the speed benefits and customizability benefits of C and C++ as memory management with the ease of use of something like Go, which has a garbage collector. Using the borrow checker lifetimes and the overall structure of the language, This memory management is performed automatically most of the times. You sometimes have to specify lifetimes, and you can use unsafe blocks to manually manage memory as well. But there is no garbage collector. This is all done at compile time. So you get that speed benefit without the security risks as well of manual memory management. In fact, if we skip down a little, 70% of Microsoft Security Response Center issues are memory safety related. So when Mozilla Research was evaluating this for the servo engine for Firefox in order to get fast and safe concurrency, fearless concurrency for a web browser, this was huge for companies like Microsoft and for Mozilla. And you can see some companies have already, in the OS and embedded use cases, have already really gone into Rust, like Ferris Systems, who came and hosted our Hack Week bootcamp for SUSE employees for Rust. Shout out to Anatol from Ferris Systems. Oxide Computer and System76 use a lot of Rust code, and Redux OS, the new Unix-like system with the microkernel written in Rust. But the elephant in the room, and I know this might inevitably happen in back channels, so I want to anticipate it first. Why not just use Go? My answer is you should, really. It's not my favorite question, but let's be realistic here. This might be a realistic question from this talk when working in cloud native. With Go, you can get faster delivery and faster onboarding. If you just want a string, just use a string. You don't have to worry about borrowed string versus heap allocated string. And you get more features with less verbosity. Go routines and asynchronous programming just come right out of the box. Whereas Rust, you have to choose a third-party asynchronous runtime, even though it comes with async STD. There's a more mature ecosystem in Go. Although Go and Rust are both adding new features frequently, as I just mentioned, Rust added async STD fairly recently, and Go modules went GA in, I believe, fall 2019. If you're not performance bound, you can use Go. It's still lightning fast, even though it has a garbage collector. It's wicked fast. If you're network I/O bound, then all you have to do is just use asynchronous programming and Go routines. If you're local I/O bound or compute I/O bound, then perhaps you might want to consider Rust, but in a lot of these cloud native use cases, you might not be. There's an existing ecosystem for Go, right? I can import a Rancher module. I can import a Helm module, client Go. All this stuff is just available. And Kubernetes and Docker are written in Go. Our whole ecosystem sort of revolves around these keystones, even though things like Docker might be replaced with Podman and Builda in a lot of use cases as well. These are sort of the bedrocks for the cloud native movement. So why Rust and Userspace? Well, we already talked about the best of both worlds, performance without a garbage collector behind the safety of the borrowing system. And there's also, we know there was always a strong focus on concurrency from the start, which can be seen in Mozilla's servo engine for Firefox. And you have all these options to avoid collisions through the lifetime system. But now let's get into other things. The result and option types are huge for me as well. The result type might seem somewhat familiar from other language. You get an object that is wrapped in an OK, and if the object does not return an error, you simply unwrap the OK and you have your value, or you get an error, which can be generic or any other kind of error. And you have to evaluate it, which is great. All error handling has to be evaluated. You can choose to ignore it, but you have to make that choice. The option type is a little more interesting, in my opinion. If you've ever seen nil pointer exception in a Kubernetes controller, you'll love the option type, because there is no concept of nil and null in Rust. You get a sum containing the value you want, or a none, indicating that the value contained in the option is, well, none. So you have to address this as well. You can choose to ignore it, but this is something that I find really great for scenarios where you might be used to handling nil interfaces in Go. Cargo, I love so much. It's replaced GNU Make for me in a lot of my Rust repos, and you can just cargo publish straight with your code, with your inline docs comments to crates.io. So it's available as a library or application, and a crate is a library application in Rust. And your inline docs comments go straight to docs.rs. So for free, you have documentation, package management, and library availability right with Cargo. And using Cargo Xtask or Cargo Run --bin, you can replace your make-like steps so that they work on Windows, Mac OS, and Linux for easier onboarding and better multi-platform support. You also have the ability to use no STD. This isn't really that important for Userspace, but just in case you needed to go to the no runtime status of Rust and a bare metal environment, you can, which is nice. You don't have to think about adding that later. Minimal standard library is a bit opinionated, but essentially, Rust has a lot of dependence on third-party packages and sort of centering around SMEs and communities to naturally figure out what's the best package for you. And I've found this really is one to the benefit of Rust. Some people come to Rust for its third-party packages that almost become more popular than the language sometimes, like Tokyo RS, which is great. Compile time reliability is true for all these previous things. Fewer errors happen at runtime for me compared to other languages, just due to all these safety mechanisms. And there's just that much more confidence in your code. Functional programming features are great. A lot of idiomatic Rust contains patterns over statements and closures over functions, and it can make some really fast, elegant code, especially that can even be faster than OO code if you're trying to avoid those paradigms a little. And the last thing that's probably the most important is the best-in-class community all over the internet, and it shows its form in things like friendly compiler messages, discussions on boards, blog posts, governance, and I really think you get none of these technical things without the community. And that might be a tad controversial, but the language is comprised of the people. Rust is the people, and the language and all these design decisions would be nothing without everybody in an inclusive, happy environment. So that is something that matters to me more than everything here, and it helped create everything here. All right, now let's explore Rust present and future in a cloud-native world. I posted 5 example projects here, 2 of which AWS uses, Firecracker especially in production. And then we have databases and search backends and even a kubelet. Some of these are very production ready and in use today, and some of them are a little more experimental. But I think the one thing is clear. It's not a matter of if Rust is valid for cloud native. It's a matter of when the next cloud native projects will come. You'll notice it's not just popular in a vertical slice. It's popular all over cloud native. And that is really fascinating. And it's something that as we evaluate more projects in Rust, we can keep in mind that, okay, what's next? It can do anything at this point. We've proven that in cloud native. So here's some things that I think SUSE might fit well into. Things like microOS with being an immutable operating system, essentially, with a lot of transactional updates and ability to have isolated execution fit well with Rust, the programming language, and its feature set. And the open build system for having fast and concurrent builds. In both these areas, C and C++ reign supreme in older Linux circles, and we can help accelerate their feature safety and security, as well as just overall speed. Because good Rust is really, really fast as well, which is, it's not only safe and secure, it's really fast. In Rancher 2.x, I could always see written in Go. However, augmenting the system with perhaps Rust applications and services installed via the Cluster Explorer UI is a huge use case I could see for Rust, as well as things like edge deployment and privileged applications for security, augmenting the existing Rancher ecosystem. Harvester out of these 4 is perhaps where I could see Rust have the most use cases. It has the newest code base. There's a potential to add micro VMs, bare metal access, advanced provisioning, and tracing, things that we've seen Rust do in a lot of other OS use cases as well. And Harvester is an infrastructure layer. So this could be a great area for Rust to go into. The sky's the limit. And the crates that propel these things, some of which you may have heard of, like WebAssembly, for ridiculously fast applications in the browser. But then we have some things like error crates, like Anyhow, that makes errors just really easy. Just give me any generic error, anyhow. And Air, which is advanced error handling that comes so easy for the user. And then we have serialization and servers. We'll talk about Actix later. Tokyo and Rayon, which is 2 of my favorite crates, which provides a synchronous runtime and a full library set to augment async STD for Tokyo, and Rayon, which is concurrent programming made easy. But we're going to talk about these last 2 here in particular. Klux, aka Eric, and I were talking over email about this talk, and Eric was so excited and retweeted it immediately. And this talk would be nothing without Eric. So huge thank you to Eric for making KubeRS and ControlRS, because KubeRS is Rust's equivalent to Client Go, and I believe it's production ready and stable. And ControllerRS is an example in the style of Cube Builder using KubeRS, which is still more of a work in progress, but we'll take a look a little later. So With these two libraries in mind, we're going to look at my experiences writing a containerized service and an operator in Rust. We'll start with the containerized service, KImager. I should probably update this thing. I did recently, and it works mostly. There's bugs. Hey, it's functional enough for this talk. And essentially, I needed to figure out whether or not a Kubernetes image was seen on the cluster for the first time, or the last pod I knew that was using it was deleted, so it was gone from the cluster, so to speak. And I didn't want any client-side dependencies other than Helm. Just install the chart and go to town, and let's log when these images appear and disappear. I used hashing and bidirectional maps to store metadata, which is a bit overkill for strings, especially since it's all entirely in memory. It probably should be using a persistent volume, but hey, this was a experimental project, so to speak. And I may replace the bidirectional maps with an undirected graph someday when I get the chance. So that's sort of how it works. We use hashing and bidirectional maps to figure out whether or not the image still exists. And using static binary building with Musel and running strip to strip away the debug symbols and putting that binary in a scratch image, we had about a 3 megabyte compressed Docker image at the end, which is pretty great. So let's take a look at the code a little. So you can see here, we have a macro at the top, and keep in mind, as we go through these code slides, you do not fully need to learn Rust. I'll walk you through at a high level just to sort of get you through the flow. So Tokyo main, that indicates to the Tokyo library and asynchronous runtime that, hey, this is the main function we want to use for our execution. And the async keyword at the front of the function indicates that this is an asynchronous function. I basically look for the Rust log variable and I set it to info if I don't have it, start the env logger to say, let's kick the logger off. And then if you see the bottom 4 lines, we have a debug statement on the first and a debug statement on the third before and after the main watcher loop that dictates how this KImager runs. Then at the bottom, you'll see the OK with the unit type inside it. That's basically just saying, hey, we don't care what the OK value contains. We just want to tell the function that we encountered no errors at this point. You can see at the top with the result type that we return, that comes from the anyhow crate. Notice how we don't specify what error we want. We just specify the unit. That means 2 things. The anyhow crate allows us to throw any generic error that imports certain traits, but we won't get into that for this talk, or that uses certain traits rather. And there's a unit. So we don't care what result returns, whether it's okay or not. We don't care about error. That's why it's result with just the unit inside. So now let's look at the KImager watch line. You can see on the inside, there's a function that's called try default. That comes from kubers. It's just like the client Go try default type functionality, where it'll either look for kube config, in cluster, out of cluster, environment variable, local kube config file. So this will work inside or outside of a cluster, or in or outside a container. And then we await it using the async await pattern. And for the sake of this talk, I highly recommend looking at some members of the async working groups blogs and such to learn more about the async await pattern for asynchronous programming. So we await to see that we got a proper config, and the question mark operator for the syntax sugar basically says, whatever error you return it to the parent calling function. So rather than handling the error right there, I'm just going to bubble it back up. So basically, if that encounters an error and it gets sent to main and it's handled as a result, the result will contain an error and the program will end, essentially, which is fine, because if we don't have a config, this program won't work. So we should basically just end the program. And now that we have our proper config, assuming that passed, we do KImager watch and we await that with another question mark operator to see if we returned an error. So now let's look at the main engine that makes this code work. You can see that just like Client Go, we use a pod API and we are not namespace because we want to see all images on the cluster. We set our list params with a 0 timeout because we never want a timeout. We just want to keep an active stream. And then we have an event driver. The event driver is in this library that I wrote, and essentially it has a method called new event that if you feed it pod metadata, as well as an enumeration that tells you whether the event was an added or deleted event, it'll essentially take the pod metadata, see whether or not it was added or deleted, and then based on the logic that happens, like the bidirectional maps that I mentioned before and hashing where the metadata is stored, it'll either log whether the image exists or does not exist anymore in the cluster. exists, in air quotes, because no pod is using it, or a pod is using it for the first time. So then if you look into the loop, we infinitely loop, and we set up a stream using the Watcher API. And then essentially we loop over the stream. We keep trying next for each object in the active stream. And you'll see the yLetSum status. This is us handling the option type. If there's a nil or none for the next object in the stream, which Rust doesn't have, we essentially just ignore it. And we just say, while some status, keep trying next until we encounter an option type for status, such as there is a value inside it. So we perform a match status on that. We perform a match pattern on that status, which must like switch and go. And if we have an added or deleted event, we add that enumeration, as we mentioned before, as well as the pod data. And then for an error event, we just simply do the error. And since this is a non-exhaustive list thus far, but I don't care about any other kind of event, I use an underscore to indicate, hey, let's just skip it. And that's pretty much it. That's the engine for the KImager. And now you can see the building looks like a lot of Go binary building, except we use Musel Rust to essentially build a statically linked binary. And we strip to remove the debug symbols and make the binary smaller. And we copy it into the Scratch container. Very similar to a bunch of Go builds with the slight bit more difficulty to use Musel Rust, but it's pretty easy for multi-stage builds. So now the second thing, last one I should probably update, this one I should probably release. This is the KRun VM Operator. It was essentially an unfinished SUSE Hack Week 2021 project. In my defense, I was on 75% vacation. I took 2 hours of every day to help out with the Hack Week Rust Bootcamp. Again, shout out to Anatol from Ferris Systems for instructing that. And the idea was to launch these isolated lightweight VMs or micro VMs, or not really micro VMs, but the buzzword's nice. And I wanted to reconcile a custom resource for information on your micro VM and launch it with KRun VM and libkrun. The problem is Kubernetes nodes required that libkrun FW be installed with the kernel. And then I needed to run the container in a privileged, I needed to run the controller in a privileged container. And I was essentially using libkrun insecurely on the host. And look, I never claimed this project made sense. It kind of defeated the point of isolated lightweight VMs, but it was fun. And we won't look at my code in particular for this. We'll look at the reconcile loop from the upstream controller RS, which I also used as boilerplate. So it was a success and it was kind of working, but it was very insecure and it's not in a state where it's ready to be released yet. So looking at the reconcile loop, you'll see, similar to the KImager patterns, we get the context from the client because we're in cluster and we have a context. We log the state with the current UTC timestamp. We grab the resource using the foo CR, the custom resource, and the foo CR this time is namespaced. And essentially, you could see API foo before we use API pod. Now we are able to use kubeRS API with custom resources. And using JSON serialization, we can add a patch you can see there in the center, specifying the API version, the kind, and the status. And then we apply, using the controller, our patch, and we set our patch params effectively. We get a patch status back, and then we await our patch status method for our foos API, and then we check if there's an error, and then the question mark operator to return any potential error. This looks very similar, and well, might not look, but it functions very similar to Client Go, and you can get started with Kubernetes operators today. So let's reflect on this a little. Tokyo and Anyhow affirm my stance on a minimal standard library. I love that third-party crates dictate, with SMEs and other heavily involved folks, dictate what are the best things to use in the ecosystem. It's really it just affirmed that experience so much, and I'm happy that that's the opinionated direction the language has taken. kubeRS felt even better than Client Go. Maybe that's partially due to result and option, but I just felt more confident in my code that I would have less runtime errors. It even felt easier and less verbose to get off the ground. And what's nice about this too, Rust, you never really have to worry, am I using the fastest language I can? Because you pretty much are, realistically, for a container. There's that bit of worry is simply gone when using this, which is also nice. But the negatives, Rust, Helm, Rancher, Helm, Tecton, I miss these Go modules. They're just simply not available in Rust. And the compiler is not known for its speed, especially on a laptop compiling static binaries in a container. It is very slow, but for good reason. It's got to do a lot of compile time, so that runtime there is no garbage collector and it's very fast. So I get it. All right, so now the last part of our presentation, how and where to get started. So the first thing I would do is install Rust UpRS and Rust Analyzer. The first helps you organize multiple tool chains, and the second gives you the best IDE-like experience with your favorite editor of choice. These two in conjunction will get you up and running with a Rust config. And then I would then read the first 12 chapters of the Rust programming language book up until the first big project. I would personally read the whole thing, but I think that first big project ties the whole intro arc together to a point where you can say, I either like or don't like this language, it is or isn't for me, and you can get started. Number 3, I would install a few Rust crates to just get a feel for cargo. Just try some things. Rip grep is really nice. Just run RG and you'll have a lot of fun potentially replacing grep for your use case. Number 4, I would try some small ideas and proof of concept with the playground. Maybe you don't want to get your local config running and you just want to try patterns, like maybe you're new to closures and pattern matching instead of using statements. There's a great website for that. Next, I would create a small CLI application using popular libraries from Awesome Rust and the Are We X Yet sites. So this would be like Are We Game Yet, where they have game engine programming and 3D modeling and stuff like that, 3D rendering. And then finally, once you get through these things, and by the way, real quick, I usually recommend the CLI because it's usually non-persistent execution. You can get a lot of value really quickly, and it's a great way to iterate and learn a lot about Rust. And trying some popular libraries, like maybe the Git2 RS library or Tokyo RS. Catch up on popular Rust bloggers and videographers. If I listed all of them, this page would be full. So I listed 4 folks who've helped me personally in my journey. John is one of my favorite Rust Twitch streamers. Jane actually helps run Rust Mentors, I believe, and reviewed one of my PRs in one of my early Rust repos, which was super nice. Amos is one of the best technical bloggers I've ever seen. And then Read Rust from Wesley Moore is a great RSS feed that you can follow for Rust. There's also a list of Rust streamers as well. Like I said, there are hundreds of folks that I could list, but these are 4 that have personally made an impact on my Rust career. So how to get started with writing cloud-native Rust? We're going to look at 3 things in particular. First is creating a Kubernetes unaware containerized daemon set deployment or job. I'll just call these all apps, those 3. An unaware one, you can run in or out of cluster and it'll behave functionally the same. And I would start with a non-persistent CLI-driven application. Maybe this takes the place of a Kubernetes job. Just ensure that you get the containerized workflow working with your app. Perhaps maybe it just posts the weather once if you just launch the job. And this is where I would learn Musel Builder or even Windows Nano Server Image if you're feeling bold. Next, I would make a Kubernetes aware containerized app. So this would be something that uses kubeRS, but isn't necessarily reconciling Kubernetes resources. Don't be afraid to use blocking calls if you're using Tokyo RS or any kind of asynchronous programming, at least to get a feel at the beginning so that your code behaves more predictably. If you want to use kubeRS, you don't actually have to write a service. You can write a job again if that works for you. And then you can follow some examples from the kubeRS repository in order to get used to using the pods and jobs API. Finally, the third thing I would do is create a controller. Fork Clux controller RS and just go straight to the reconcile function. Don't worry about the rest of it at first, I would say. And even if you don't want to focus on the controller, maybe all you want your controller to do is when you see a CR resource created, you just launch your job that you made from the last step or the step before. You don't have to focus on making a super advanced controller if you just want to use the controller to launch other things. And then maybe after that, you can start getting into advanced use cases with your controllers and operators. And that's pretty much it. Thank you very much for listening to this talk. Like I said, you can tweet at me at nickgerashacks, or you can email me at my SUSE address as well, nick.gerace@suse.com. And hope you get started with some cloud native Rust. I think the future is very bright, and thank you very much for listening.